All right, now that we have introduced rotational motion, rotational quantities, we want to start to think about connecting quantities from the past, putting them into context with rotational motion. And so the first thing that we want to think about is rotational kinetic energy. So I've got an example here. I've got a mass m traveling around this circle. So the translational speed is just given by v here. So kinetic energy, the translational kinetic energy, 1/2 mv squared. And what I want to do is I want to take the relationship between the translational speed and the angular speed, right? So if this object is traveling around the circle, we can describe that with an angular speed. So I'm going to substitute the translational speed for the angular speed multiplied by the radius. That's the size of the circular motion. So I'm going to swap this in here. And so I'm going to rearrange the terms, and I'm going to get this 1/2 mr squared times omega squared. This is the kinetic energy. So it's the same kinetic energy term, but now it's written with rotational parameters or quantities. I've got omega rather than the translational speed. And so if you think about, well, what if I had, so in the first example I had one object rotating or traveling around in a circle. So here I have 4. I've sort of separated them out, and they're all going around at the same angular speed. And so what that means is that the one out at the edge, which is orbiting at the largest radius, has the largest translational speed, and then as you get closer and closer in radius, the speeds are smaller and smaller. Again, that's because of this relationship. Omega is constant. As r changes, the translational speed changes. So I've got 4 objects here. So if I want the kinetic energy of these 4 objects, I just have to add up the individual kinetic energies of all 4 objects. So I'm writing this out very detailed. So here's each of the kinetic energy terms. Again, this is 1/2 mv squared, the translational speed. And then I'm going to swap out what I did up here. I swapped out v for omega r, and then I separated the terms, and so that's what I'm doing here all at once, swapping in omega r and then regrouping the terms. Notice that omega is the same in all 4, and the mass and the radius are different for each of these because the masses are different and they're orbiting at different distances from the center of the circle. And so if you look at this in general, then the kinetic energy of n number of objects that are undergoing rotational motion is just the sum of, so 1/2 times the sum of mr squared. So m sub I, r sub I squared. So that's just, you cycle through each of the particles that you're considering, and then multiplied by omega squared. So 1/2, sum up all of these mr squared terms, and then multiplied by omega squared. So this allows us to define a new quantity, which is known as the moment of inertia. And if you look up here at my kinetic energy term, that's what we're going to define as I, the moment of inertia. The moment of inertia is the rotational equivalent to mass. So you're going to see next week when we start talking about torque and how you cause the rotation of an object to change. It's going to be connected to the net torque that's acting on an object. And when there is a net torque acting on an object, the angular acceleration that an object experiences is going to be proportional or related to the moment of inertia of the object. Just like when there's a net force on an object, the net force is equal to ma, so it's proportional to the mass of the object and then multiplied by the translational acceleration. So moment of inertia, I, is just the sum of all of these terms, mi ri squared. So every mass that you have, multiply that by how far from the rotation axis you're considering. So r is how far from your rotation axis, and then square that r, and then you add up each of those terms. That's what the summation sign means. So the units for moment of inertia are just, well, kilogram and then meter squared. So kilogram meter squared is the unit for moment of inertia. Again, moment of inertia is going to serve as the rotational equivalent of mass. And if you look at what happens when I go from my kinetic energy expression and I substitute in for this the moment of inertia, right, because this is what I'm defining as I, then the kinetic energy for a rotating rigid object is this expression right here, 1/2 I omega squared. And that should strike you as familiar, right? It looks an awful lot like 1/2 mv squared, where I is the rotational equivalent of mass, omega is the rotational equivalent of translational speed. And so if you have an object that is both rotating and moving translationally, then the total kinetic energy is just going to be the sum of each of those types of kinetic energy. So now that we're going to allow objects to rotate, when we talk about kinetic energy, what we really mean is what's the kinetic energy due to the object rotating, and what's the kinetic energy due to the object moving translationally. And so then you just add these two terms together, 1/2 I omega squared plus 1/2 mv squared. And these terms don't both have to be non-zero. If the object's not rotating, then there won't be any rotational kinetic energy, and it'll just be a 1/2 mv squared term for the kinetic energy. You could also have an object that's not moving translationally, just rotating, and then you would have only rotational kinetic energy to account for. So we have this new quantity, moment of inertia, so that's MOI. But we should think about how do we actually calculate the moment of inertia for a given set of objects, and go through a few examples. So first off, if the number of objects or masses which are point-like, so this is sort of a simplified approach, if there's a finite number of them, that is, you can add them up, then the moment of inertia calculation is just what we looked at in the previous portion of the video. Just add up all of the mr squareds. Right, so if you've got 3 point masses, then you'll have 3 terms here to add up. Now, if your object is extended, so the mass is extended across sort of a real object, then it's not a point-like object, it's not a finite number of masses, so what you need to do is you need to integrate. So you need to evaluate the integral of r squared dm, where dm is the infinitesimal sort of chunk of mass, and you need to add up all of the chunks of mass multiplied by how far away those chunks of mass are from the rotation axis that you've identified. So let's look at an example here to show how to do this for the finite collection, and then also how to do the integral. So here's my finite example. So I've got 2 masses, a 5 kilogram mass over here on the left, and a 2 kilogram mass over here on the right, and the 2 masses are separated by 2 meters. And what I'm going to do is I'm going to find the moment of inertia about this axis, so about this x1 axis. So that would be these 2 objects. I've drawn this dotted line here so we can pretend like they're just connected with a massless rod or something like that. So we're going to think about rotation axis here. So we want to figure out the moment of inertia about this location. And then we also want to figure out the moment of inertia about this axis, right, just to show you how to do this. So let's start with axis 1. And so to calculate the moment of inertia, the definition is just add up all of the m times r squareds. So I've got 2 objects here, so I'm going to have 2 terms when I write this out. No matter the order here, but I'm going to start with the 5 kilogram mass. So I've got a 5 kilogram mass, and then I look at the picture. How far away am I from the rotation axis that I've identified? Well, I'm 1 meter away. And so I've got my mass multiplied by r squared. And then I'm going to add the next term. So the next term is the 2 kilogram mass. How far away are we from the rotation axis? Again, 1 meter. And so I've got these two terms that I've got to add up. And so I get 7 kilogram meters squared for the moment of inertia when I'm rotating about this axis through the center. Now, when I change my rotation axis, I'm going to have to redo the calculation. Same idea though, I'm going to add up all of the mr squared terms. So now I'm going to pick this location as my rotation axis, so 5 kilograms, and then how far away is the 5 kilogram mass from the rotation axis? Well, 0 meters. It's actually located on the rotation axis. And then I've got plus, now I've got the 2 kilogram mass. Now how far away is that? Well, that's 2 meters away from the rotation axis. And so now this term is 0, but then this adds up to be 8 kilogram meters squared. So depending on what you choose for the rotation axis, the moment of inertia, the calculation will change, because it depends not only on the masses in your problem, but then also how far away the masses are. So in rotation axis 1, they were both the same distance away from the axis, but with rotation axis 2, the 5 kilogram mass had a distance of 0 from the rotation axis, whereas the 2 kilogram mass had a distance of 2 meters. So when you go to calculate moment of inertia, you have to take into account not only the mass, but then where is the mass located relative to your rotation axis. So how does this play out if we've got a continuous distribution of mass rather than a discrete collection of point masses? So let's look at this. I've got a rod here. So this is a rod of length L, total mass M, and I'm going to rotate the rod about this axis over here on the left. And so I want to figure out the moment of inertia of this rod about that axis. Now, this is a uniform rod, which means that the ratio of M over L, so if I took any chunk of the rod, let's say this much of it, then if I took the ratio of how much mass was contained there divided by the length that was there, I would always get the same value no matter how much of the rod I took a chunk of. And so I'm going to write the ratio M over L as a constant. I'm just going to call that lambda. Lambda is a typical mass per unit length constant. All right, so this just represents the mass per unit length of the rod. So if you multiply this by the length of the rod, you get the amount of mass that you're considering. All right, so let's look at the integral. Right now that we've got this continuous distribution of mass as opposed to the discrete distribution, we need to integrate rather than sum, and we're going to integrate r squared dm. Now, r squared is how far away, so just think about breaking up this rod into small chunks of mass. So r here is going to correspond to how far away from the rotation axis each of those chunks is, and dm corresponds to how much mass is in each one of those little chunks. Now, I've got this set up so that I've got an x-axis here. So x equals 0 is where I'm starting. The rod ends at x equals L. And so instead of r, I'm going to use x as my variable. And I'm going to be integrating from, well, x can go from the left edge, which I'm calling 0, all the way to the right edge, which I'm calling L. So those are my bounds. And then the little chunk dm, the little chunk of mass, remember, the mass over the length is a constant value lambda, so dm over dx has to equal lambda. And so dm is going to equal lambda dx. And that's, so I've swapped out dm for lambda dx. Now, lambda is a constant, so that just will come out of the integral, and I'm going to integrate x squared dx. So that gives me 1/3 x cubed. And I have to evaluate the integral over the bounds, so the length of the rod. So that just works out to be plugging in L, because when we subtract the 0 term, it doesn't contribute anything. And so here's our value, and remembering that lambda equals m over L, I'm going to substitute this in for lambda. One of the L's is going to cancel out, so I get left with L squared, and then the total mass here. And so this is the moment of inertia of a uniform mass rod rotating about the end of the rod. So rod of length L, moment of inertia about the end of the rod. 1/3 the mass of the rod times the length of the rod squared. And what I would encourage you to look at is figure 1020. That's a figure that shows the moment of inertia for a variety of different common objects, rods, spheres, disks, and the moment of inertia about different rotation points, whether it's the end of the rod or the middle of the rod. Again, changing the rotation point or rotation axis is going to change the moment of inertia calculation because the mass is now a different distance away from the rotation axis. And so the last thing that I want to mention here is that if you know the moment of inertia about the center of mass of your object, then you can immediately find the moment of inertia some distance d away using what's known as the parallel axis theorem. And so the parallel axis theorem says that the moment of inertia, a distance d away from the center of mass, is just the moment of inertia at the location of the center of mass. So in this example up here, that would be finding the moment of inertia right through the center here. So that, if I had done the calculation from here, evaluated the integral from these bounds, I would have got the moment of inertia about the center of mass. And then I would add to that md squared. So I'm a distance L over 2 away, so I would add to whatever I get for the moment of inertia for the center of mass, I would add m L over 2 squared. And when I add those together, what I'll end up getting is 1/3 ml squared. So the parallel axis theorem allows you to quickly determine the moment of inertia at locations that are a distance d away from the center of mass without actually having to redo the entire integral. So you can grab this value, figure 1012, and then add the additional term, which corresponds to being a distance d away from the center of mass, and you can immediately get the moment of inertia for your specific problem. The last thing I want to mention is that if you have a compound object, so maybe you have a rod connected to a sphere or a rod connected to a disk, and it's rotating, well then to calculate the moment of inertia, you just treat the objects separately. So let me just show you what I mean. So let's say you've got a rod and then a sphere, and maybe this thing is rotating about that point. And so you want to know the moment of inertia about this rotation axis here. Well, you can do that by figuring out the moment of inertia due to a rod of length, whatever this length is, rotating about the end, and then also find the moment of inertia of a sphere rotating this distance away from the center of mass, and then you would add those two moment of inertia together to give you the total moment of inertia of this compound object. Right, so you can treat the object separately to calculate the moment of inertia, and then you just add the results together to get the total moment of inertia of your compound object. And that's pretty much it for the idea for moment of inertia. And we want to keep in mind that the moment of inertia is going to be incredibly important as we start thinking about Newton's second law for rotation and how the net torque is equal to I alpha. But it's also important for thinking about rotational kinetic energy. Remember that moment of inertia is going to serve as the rotational equivalent of mass moving forward.